Welcome. In this video, we're taking a closer look at how we move from observation to forming a hypothesis. We will explore three key ideas: observation, noticing patterns; hypothesis, forming explanation; and theory, building broad understanding. We discuss clear testable hypothesis and look at a real-world example. Dr. Ignaz Semmelweis, who uncovered the cause of childbed fever, not through opinion, but through careful observation and bold hypothesis. So let's see how curiosity becomes science. Let's break down how scientific reasoning typically starts, with an observation. This is the systematic noticing of patterns or anomalies. It requires clear thinking and structure. Try this. List all the objects in your immediate vicinity. But what counts as an object? Where does your immediate vicinity end? Even simple observations require clear definitions and rules. In computing, an example of an observation might be, this algorithm slows down when the input size gets large. That brings us to the next step, the hypothesis. A hypothesis is a testable explanation for an observation. It's a tentative, unproven idea that applies to a specific range. So in our example, the hypothesis might be the cache miss rate increases with input size. It's focused, it can be tested, and it offers a potential explanation. Finally, we have a theory. A theory is broad, well-developed, and supported by strong evidence. It doesn't just explain what happens, it explains why. For example, in computing systems, as input size exceeds cache capacity, miss rates increase due to reduced spatial and temporal locality, especially in fixed-size cache architectures. That's not just a guess. It's a theoretical explanation supported by repeated testing and deep understanding. In short, we observe patterns, we form hypotheses to explain them, and over time, we build theories that give us reliable, powerful insights. There's no structured process of coming up with an hypothesis. So what makes a bad hypothesis and what makes a good one? A bad hypothesis is usually too vague, broad, or even tautological. Basically, it doesn't say much or just repeats itself. For example, users like feature X. Well, maybe, but what does like mean? Who are the users? How do you measure it? That's where good hypotheses stand out. A good hypothesis is specific, measurable, and most importantly, falsifiable. It should be possible to prove it wrong through testing. Here's a better version. Users who use feature X will report a satisfaction score of at least 4 out of 5 on a standardized usability questionnaire. Here, it's clear who the users are, how we'll measure their satisfaction, and what the success criteria are. So when crafting your own hypothesis in usability testing, system performance, or anything else, aim for clarity, precision, and testability. If it can't be tested or proven wrong, it's probably not a real hypothesis. For over 1,000 years, the Ptolemaic model dominated astronomy. Earth stood at the center of the universe. It was a neat explanation of all the visible motions of celestial bodies, at least the ones known at the time. But there was a problem. Planets didn't always move as expected. For example, Mars sometimes appeared to move backwards in the sky. To fix this, Ptolemy added epicycles, small circular loops on top of the main orbits. It worked, kind of, but it made the model increasingly complex. Then came Copernicus with a radical different idea. What if the sun, not the Earth, was at the center? In his model, Mercury and Venus orbit closer to the sun, and Earth itself moves, rotating and revolving. It was a massive paradigm shift, not just a tweak, but a new way of thinking about the universe. And it led to more powerful hypotheses and tests. Later, Kepler refined the model by introducing elliptical orbits, which made predictions even more accurate. This transition from Ptolemy to Copernicus and then to Kepler is a classical example of how observations challenge old models and how new hypotheses can trigger a scientific revolution. It also shows how science values simplicity, accuracy, and better explanations, even if they challenge long-held beliefs. Ignaz Semmelweis was a 19th century physician and an early pioneer of antiseptic procedures. Long before germ theory was widely accepted, he reduced the deadly toll of childbed fever in hospitals. Here is what he observed. His hospital had 2 maternity wards, one run by midwives, the other run by doctors and medical students. Women assigned to the doctor's ward were dying at much higher rates. Semmelweis noted that patients were allocated to each ward on alternating days. So this couldn't just be coincidence. What was different? Not the food, not the linens, not the birthing positions, not the treatment of staff numbers. The only consistent difference, doctors were performing autopsies and then attending birth without washing their hands. Semmelweis has hypothesized it wasn't the wound that killed, it was cadaveric material carried on the hands of the medical staff. At the time, the dominant theory was miasma, that disease spread through bad air. But Semmelweis put this idea to the test. In 1843, he introduced hand washing with chlorine, a substance that removes organic matter. The result, mortality has dropped dramatically. His work didn't just reduce deaths, it marked one of the earliest examples of using data systematically, like a modern epidemiologist. He connected observation to a hypothesis and then tested it, just as the scientific method teaches. Even though his ideas weren't accepted in his lifetime, today Semmelweis is rightly celebrated as a scientific pioneer who saved lives. The scientific method is a 3-step process. Observe, speculate, and test. Step 1, observe. You start with a clear sense of the facts. In this case, physicians noticed that some hospital wards had much higher death rates than others, especially those staffed by doctors rather than midwives. And those rates spiked even more after doctors examined women right after working with corpses, like in the tragic case of Kolechka, a colleague of Semmelweis who died with similar symptoms. Step 2, speculate. Propose an explanation. What could possibly explain this disturbing pattern? The hypothesis, cadaveric matter transferred from corpses to patients by doctors' hands, was causing the illness. Step 3, test the explanation. To find out, doctors began washing hands with a chlorine solution before examining patients as an experiment. The result, childbed fever cases dropped dramatically. A simple test based on a specific hypothesis transformed medical practice and saved lives. So what is science really? It's the activity that aims to understand why things happen the way they do in the natural world, in systems, or even in code. And it does that by applying the scientific method. We observe, identify what we don't yet understand, and then propose test explanations. It's not perfect, but it works and keeps getting better. We started by defining key terms. Observation is where science begins with noticing patterns, over-testable explanations, yielding a theory that is broad, well-tested explanation that's supported by repeated evidence. Next, we looked at what makes a good versus a bad hypothesis. A bad hypothesis is vague, broad, or untestable. A good hypothesis is specific, measurable, and falsifiable. Then, we saw how science can evolve through paradigm shifts, systematically observing, hypothesizing, and concluding, using the example of Copernicus and Semmelweis.